share my screen. Oops, wrong button. Apologies. All right, can everyone see my screen okay?
Yes, but you spelled my name wrong.
Oh, I did. I didn't on the next. I did it everywhere, but I'm not quite sure how I did that. I'm so sorry. All right, everyone. My name is Donna Shillington. I'm from Northern Arizona University, and I'll be convening our active source poster session today. So we'll have brief talks, 3 minutes long from each of the people you see here, hopefully with other names spelled correctly. And then afterwards, we'll have some time for questions and discussion. So if you want to start popping questions in the chat, that's good. But otherwise, we'll just hold the discussion until after all the presentations are through. Yeah, hopefully, as I said, they'll be about 3 minutes long. And so then that will give us a good 30 minutes of time for discussion from 3:30 to 4:30 p.m. Eastern time. And once we come to that discussion time, if you could just write in the chat, if you have a question, either you can type your question and I can read it, or you can just indicate you would like to ask a question. And that'll help me keep up with, you know, in what order people were volunteering to ask a question and track things that way. So yeah, as opposed to the hand raising, which is a little harder to keep track of. So hopefully chat function will work well. So yeah, our agenda here is to go through this fabulous set of talks that you see here. Hopefully folks have had a chance to look at some of these posters already in advance. I also wanted to point out that there are other posters that are covering active source seismology and the kind of open session, which doesn't have an oral session associated with it. So I'd encourage you to look there. And of course, it's active source seismology being so important to sprinkle through all of the sessions at the symposium. So, all right. So with that, and with apologies to Gail for the misspelling on the first slide, I will hand it over to Gail to give the first 3 minute summary.
Okay, great. So I'm presenting a poster on Chicxulub. So we are mapping the peak ring, the Resurge deposit, and the top of melt at the Chicxulub impact structure. And my co-authors are Joanna Morgan and Sean Gulick. So we're using the full waveform inversion technique, FWI. And so this first slide summarizes how it works. So at the top left, we have, is Donna gonna do the arrow for me? At the top left is observed data from a streamer gather. And right below it are synthetics made with a starting velocity model. And then at the bottom, you can see how the synthetics look with our waveform inversion model. And then the other two images that we see are showing the difference between the starting model and the final model. And what we're doing there is we are interleaving the observed and the synthetic data. So
Uh-oh, you've frozen, Gail. We'll wait patiently for your internet to recover. Gail, are you there?
I'm back. I was wondering if Sean just took over.
We can invite him to do so. Sorry about that. Okay, great.
Okay, so what we're showing are we're interleaving the observed and the synthetic data. So the top middle, you can see a lot of kind of chatter where we're within half a wavelength, but not quite right. And then the bottom shows the difference with the full waveform inversion. So you really can't see the difference between the observed and the synthetic, I hope. Okay, so that's the technique. So the next slide.
Has the slide advanced?
I don't see it.
I do.
Oh,
Yeah,
there
I
it is.
see it. Yeah.
Okay. And so now we can see our beautiful image. So what we've done here is we have the seismic reflection data that we've converted to depth using our full waveform inversion velocities. And then we've overlain on top of that the velocities. So even if you're not familiar with impact craters, there's a lot of cool features here. So what's labeled as the peak ring, this is fractured granite. And so you can see the velocities are green compared to what's adjacent. So those are lower velocities. So the fracturing has caused a lot of porosity and lowered the velocity of granite. And then to the right, you can see something labeled a melt sheet. So that's the, when you have an impact, you have so much pressure that you melt the rocks and form this melt sheet. And we can map it both with the reflection data and the velocities. And then on the far right, you see a perturbation in the sediments. And we think that's an upflow zone associated with a hydrothermal system at the edge of the melt sheet. So you can see more details at my poster.
Excellent. Thank you so much, Gail. All right, our next speaker is Adam Robinson, who's from the University of Southampton. So.
Hi, thank you, Donna. Thank you, everyone, for coming along. So the work that I'm presenting here is work which is looking at a location of active fluid flow, specifically the flow of methane gas in the very shallow subsurface in a region of the North Sea. So on screen, on the top right, you can see an image of the methane plume, which has been observed using multi-beam echo sounders. And this is observed to be coming from a pockmark on the seafloor, Scanner Pockmark. And the rate of methane escape at this location has been measured at around 1,600 to 2,600 kilograms per day of methane. Looking in the subsurface over on the left-hand side, a spark of seismic reflection image, we have a well-characterized stratigraphy here, and in the subsurface highlighted by the dashed vertical white lines, we have a region of acoustic blanking, which is due to a gas accumulation above. So at the location, the green line, and we see high seismic amplitudes in there. This feature is a feature called a seismic chimney structure or a seismic pipe structure, and we're also working to understand above how the gas from the top of this seismic manifestation of a chimney structure then travels up through fluid flow pathways and escapes the seabed. And the way I'm doing this is using shear wave splitting, so looking for vertically aligned fractures or horizontal transverse isotropic systems, which you can see the idealized versions of. And our motivation for doing this is partly related to active fluid flow, but it's also has relations to potential carbon capture and storage operations, particularly the risk of loss of fluid containment. And in a recent, just out a few weeks ago, open access paper by myself et al, we talk about the context of the experiment in relation to CCS. If you could move on, Donna. Oh, is that all I gave you? Sorry, I thought there was another slide there. I'll briefly say then, you can see in my posters, my work is on looking for evidence of shear wave splitting, and we're definitely able to identify that in some locations of the shallow subsurface, and looking at somewhere in the region of 2 to 3% anisotropy. And I'm currently in the process of working, doing the various corrections that are required to progress the imaging down through the sediment column, with an aim of characterizing the potential fractured nature of the region that's allowing this gas to permeate through. Yeah, yeah. Sorry, did you say you'd lost me?
No, you're fine. I think we're losing Donna.
Right. Okay. That's all I wanted to say on this.
Right. Thank you so much. I think I may have had a technical failure there, so apologies if I froze.
That's okay. No problem. Thank you very much.
Thank you so much, Adam. All right. Next, we'll move on to Yu-Huan Hsieh. With her, who's a PhD student in Earth and Atmospheric Sciences at University of Houston. And her talk here is Discovery of a Thin-Skinned Retro-Wedge Thrust Belt of the Taiwan Arc Continent Collision by PSDM of Legacy Seismic Reflection Data. So Yu-Huan, I'll hand it over to you.
Thank you, everyone. Yeah. And next slide. Yes. Thank you, everyone. Today, I want to share with you our new discovery and interpretation of a thin-skinned retro-wedge thrust belt in Taiwan Arc Continent Collision by predictive migration of legacy seismic reflection data. And our study area is Taiwan in the and Taiwan Arc Continent Collision is one of the fast pre-converging margin in the world. The Philippine Sea Plate moves northwestward with a converging rate around 9 centimeters per year and collide with the USR plate. And the right-hand side is the bathymetry, the high-resolution bathymetry of the retro-wedge thrust belt in the Taiwan Arc Continent Collision zone. And about 3 centimeters per year pre-converging rate is constrained in this small submarine thrust belt. So this is really important for understand our continuing creation process in the submarine thrust belt. Next slide. Thank you. And our study, in this study, we reprocess seismic reflection the data to predictive migration profile, so we can know better geometry of the thrust belt. And this seismic data was collected by Lance's 2009 survey in offshore eastern Taiwan, where it's run across the entire offshore eastern Taiwan thrust belt. Next slide, please. And we also integrate the seismic profile with the local tomography. So based on the tomography, we realize that that is a secondary subduction zone where the forward lithosphere subduct during the arc continuum collision. The secondary subduction zone is concerned to the 6 centimeters per year pre-converging rate. Of totally pre-converging rate 9 centimeters per year. Then, so it's really important. Then we integrate the seismic profile with the local tomography imagery, and we found out that only when the forward lithosphere completely subducts into the mantle, the retro-wedge thrust belt start to develop and form a thin-skinned retro-wedge thrust belt backside of the volcano arc. And please go to my poster session and check out my 10-minute presentation videos, or drop me a message. I would like to discuss more and receive more suggestions from you. Thank you.
Thank you so much. All right, our next presentation will be given by Zhehao Li, and he sent us a video to play. And so let me exit here and play that. So hopefully you can all still see my my screen here, and I believe that you can adjust the volume on your side if you find that it's too quiet. I have it turned all the way up. So with that, I will begin.
Thank you, Dr. Shellington.
Hello, thank you for tuning into my poster presentation today. I'll briefly give an overview of my poster, and I welcome any comments or suggestions you may have. My poster involves bubble pulse artifacts that exist in marine acquisition and their attenuation. During cruise TN373 with Dr. Zhou and Dr. Sager, we found this to be an important issue during interpretation, processing, and acquisition of seismic.
Dr. Shalinton, I don't think I can hear the sound. Or is it just me?
No, it was me too. It was going fine,
Yeah.
I think. And then it stopped.
Maybe this is my internet connection here at work. Let me, can you hear me now?
Yes. I think you muted.
Oh, possibly. Yes. Okay. Thank you. It was loud noises outside, but of course that's muting the video too. So I will back up. Apologies, everyone.
Facts. What is the purpose of this research? And finally, how is the research conducted? First, we'll take a look at the acquisition geometry of our cruise TN373. Sources were composed of two 105 cubic inch GI guns. However, strong bubble pulse were still observed during acquisition due to the oscillation of the bubbles. Upon release of the pressure from an air gun, the impulsive energy propagated through the medium. However, as the initial air bubble expands, the air pressure inside the bubble quickly drops. The expanding gas shell cavity collapses and causes rebounds, forming the first maximum and the second maximum. This generates unwanted bubble pulse after the initial impulse and produces artifacts during imaging. In Figure 3, 3 air gun arrays were fired at the depths of around 7 meters, and their waveforms and energy spectra are shown. In Figure A, a single 250 cubic inch air gun. In Figure B, 7 1,350 cubic inch air guns. In Figure C, 8 750 cubic inch sleep guns. Since our source's geometry was most similar to that of Figure A, our data exhibit similar features of secondary bubble pulse and spikes in the energy spectra. In Figure 4, we show the pre-stack data in common shot gather domain. Figure A shows the data before bubble pulse removal. We can see the secondary bubble pulse after the first arrival around 100 milliseconds. We plan to attenuate the bubble pulse by exploiting the periodicity of multiples and removing the predictable part of the wavelet using predictive deconvolution. Matching filter can also achieve similar results by identifying the presence of a given waveform in the presence of noise. Figure B shows our attempt to attenuate bubble pulse using predictive deconvolution. Figure C is our attempt to attenuate bubble pulse using matched filter. We observe more added noise when using deconvolution. In Figure 5, we show the post-stack data in common midpoint domain. Figure A shows the data before bubble pulse removal. Figure B is our attempt to attenuate bubble pulse using predictive deconvolution. Figure C is our attempt to attenuate bubble pulse using matched filter. This is a comparison between matched filter and predictive deconvolution. We found matched filter were able to attenuate bubble pulse better than predictive deconvolution during our processing. We conclude that bubble pulse artifacts can exist during interpretation, processing, and acquisition if not attenuated properly. Optimal airgun array that's composed of multiple airguns that can cause constructive interference of initial impulse and destructive interference of the bubble pulse can circumvent the need to remove bubble pulse during further processing. However, in the absence of multiple airgun resources, our initial processing results shows that the matched filter can perform better than predictive deconvolution during bubble pulse removal. For our future works, we want to validate these methods using a more numerical approach and to explore other methods that may be able to attenuate and detect the bubble pulse. Thank you for your time.
Excellent, thank you. All right, and our next presentation will be given by Edgar Contreras, who's a PhD student in geophysics at the University of Houston. So Edgar, take it away.
Thank you. Next slide, please. Okay, so today I'm going to be talking about evidence of rifting on Valdivia Bank based on 2D reflection seismic data observations. This is the same seismic data that Zhehao worked on, the one he just covered. And just a brief overview, Valdivia Bank is an oceanic plateau in the Southeast Atlantic that's part of the Walvis Ridge. This was formed by plume volcanism around 80 million years ago near the Mid-Atlantic Ridge. Now in 2019, we acquired new 2D seismic reflection data, and this was really some of the first large-scale geophysical imaging that we have over this specific plateau called Valdivia Bank. Now these preliminary observations really surprised us because they reveal two extensive rift grabens, one that trends north-south, another one that trends southwest to northeast. And these are going to be shown on lines VBO2 and VBO6. You can see these lines on figure 2, which is the bathymetry map, and you see the seismic lines overlaid. We collected 13 lines in total. And the processing, Zhehao covered a little bit, and he covered it better than I probably could. So I'll leave that as it is. You can find that more on that on my poster. VBO2 and VBO6, you can see these two rift grabens. You see those tilted fault blocks. I'm going to cover that in more detail on the next slide. And then you also see the cross-section profile across the seamount. It's a very interesting profile because it's asymmetric, and on the east side, which is the right side, you have relatively subhorizontal faulted basement, then you have a rift that cross-cuts the middle of the summit, and then you have shallow slopes and mass transport deposits on the west side. Next slide, please. So here are interpretations of these two rifts. These are, of course, preliminary interpretations. In VBO2 on the left, this is the rift that trends southwest to northeast. You see these pre-rift, syn-rift, and post-rift sediments broken up. Now, we were surprised to see this thicker pre-rift sediment package, considering this was formed around 80 million years ago at the Mid-Atlantic Ridge. So there was some sedimentation that continued as these tilted fault blocks continue to be tilted. And then you see VBO6 on the right, and you have a very similar rift structure to the one on VBO2, being that it's in a different area of Valdivia Bank. Now you don't really see those pre-rift sediments as well on VBO6. So this also gives us clues about the relative timing of these two rifts. And from this we can conclude that these two prominent rift grabens of Valdivia Bank are more complex than previously understood or previously ever really seen prior to this cruise. And also that Valdivia Bank is an asymmetric plateau that's has subhorizontal faulted basement on the east side with shallow slopes on the west side, as I mentioned earlier. And this can be attributed to just the rifting history, the onset of rifting followed by a gradual decline as the Mid-Atlantic Ridge interacted with the plume and as the seamount continued to diverge away from the Mid-Atlantic Ridge. Feel free to check out my poster, and if you have any questions, don't hesitate to message me or bring them up later today. Thank you.
Great, thanks so much, Edgar. All right, our next talk will be given by Rob Allen, who's a postdoctoral researcher at Imperial College. Uh-oh, did I freeze for a moment there?
Not you this time.
No, you're fine this time. Yeah.
For once.
Is Rob here?
Is Rob with us? I saw him earlier. Give him a minute or two, and then maybe we'll move past Rob and hope to come back to him if he doesn't join us. I think I've seen him coming back.
Yeah, sorry, I lost internet at kind of the worst possible moment there.
Quite dramatic timing, so.
Yeah, it was. So yeah, hi everyone. My name is Rob Allen. I'm a postdoc at Imperial College, and this is some work that I've been doing as part of Project Voila, which is a large project funded by NERC in the UK to kind of understand what the role of subducted volatiles is at the Lesser Antilles and how volatiles in the slab kind of relate to other subduction processes. Some of you might have seen Steve Hicks's talk in the previous session that came from the same project. And my poster particularly deals with this question of outer-rise hydration. So outer-rise hydration is a process that's been the topic of quite a few talks at this symposium already. This idea that as you approach the subducting trench, bend faulting across the outer rise creates pathways for water to access down into the lower crust and upper mantle. And in this way, we form a lot of hydrous minerals, particularly serpentine in the upper mantle. And this is responsible for a lot of the water that gets carried down to subarc depths within the slab. Now, we've got quite a lot of these studies now, but there's still quite a lot of uncertainty about what kind of the key guiding features are that determine how much hydration occurs. Some studies suggest it's the amount of sediment on the incoming plate. Some suggest it's the style of faulting across the outer rise. And so it's really important that we continue to sample more diverse systems to really kind of understand what the key parameters are here. And the Lesser Antilles is quite an important case study in that respect, because it's one of only 2 subduction zones that subducts slow spreading Atlantic oceanic crust. And unlike the vast majority of these studies, which take place in the Pacific, where the lithosphere is either intermediate or fast spreading, obviously in slow spreading crust in the Atlantic, we might expect quite a significant difference in the structure of the slab. So where the lithosphere is very magmatically poor when it's spread, you might expect a very thin crust. You might expect lots of faulting to be already present in the crust, formation of core complexes, detachment faults. And there was really this question of how crust of this type would interact with this outer rise faulting process when it arrived at the outer rise. And so we acquired these seismic profiles that you can see here. So these are 2 175 kilometer profiles across the outer rise of the Lesser Antilles, both MCS and wide angle data. The wide angle data is acquired into a network of 46 OBSs from the German DPAS and UK OBIC pool, spaced about 4.5 kilometers apart. And you can see the MCS profile down in the bottom left with the incoming plate on the right-hand side, and then it's subducting down below the accretionary prism in the west. And so this OBS data, the wide angle survey, was picked and then inverted for the final VP model in Tommy 2D, the software of Korinaga et al. And you can see our final VP model and the velocity anomaly plot below on the right. And essentially what we see as we approach the trench are 2 distinct changes in the velocity structure. One on the right-hand side coincides with the onset of outer rise faulting in both bathymetry and also imaged in the MCS section. And you can see we have this clear reduction in velocity in the lower crust and upper mantle, where these dark blue colors give way to the lighter colors at around 132 kilometers. And then from about 95 kilometers, we have this very kind of profound change in structure. Most clearly, you can see this in the shallowing of the red MOHO line. And the crust changes from about 7 kilometers thickness to about 5. And we interpret this as a transition from far more magmatically robust crust on the left-hand side to this far more tectonically controlled kind of slow spreading, asymmetric spreading crust in the west. And you can see that within this crust, this slow upper mantle anomaly, this red slow velocity in the upper mantle, is really quite profound. So we're seeing velocities in the upper mantle there potentially as low as 6.5 or 6.6 kilometers per second, which would represent a really high level of serpentinization beneath the outer rise, potentially as much as 40% serpentine in the upper mantle. And essentially we interpret this as the fact that this crust is already so heavily faulted because of this kind of slow asymmetric spreading that there's really a lot of pathways available for water to access the upper mantle. And this raises this quite interesting point, which is that in slowly accreting lithosphere of this type, in a slab such as that of the Lesser Antilles, you probably have quite significant changes in the level of hydration within the slab according to the accretion style of the crust. So in the more magmatically robust sections of the slab, like on the eastern part of our profile, we see a level of hydration very similar to the pre-existing Pacific examples. But in the more tectonically accreted crust, really very high levels of hydration. And obviously this has implications for things like the distribution of earthquakes and volcanoes. And that is my presentation, and there's more in the video on the website. Cheers.
All right, thank you so much, Rob. Now we'll move on to our next speaker, who's Shuoshuo Han, a research associate at University of Texas Institute for Geophysics.
Thank you, Donna. So in this presentation, I'm showing you the many double BSRs across the northern Hikurangi margin that we have imaged using the 2018 NZ3D seismic volume, as shown here. So our 3D volume covers a survey area that is 14 kilometers by 60 kilometers. And from this volume, we have imaged a lot of structures, like including faults and plate interface, but today I'm focusing on the BSRs. So BSR, or bottom simulating reflection, occurs in the upper few hundred of marine sediments, and they usually follow the seafloor as shown in this image, and they cross-cut those sedimentary layers. The BSRs are, most of the BSRs are associated with gas hydrate, and they are believed to mark the base of the gas hydrate stability zone. The BSRs are widely observed along continental margins, but double or multiple overlapping BSRs are relatively rare. So, and their formation mechanisms are not well understood. In our volume, we have observed a primary BSR covering a large portion of our 3D box, but in addition, we also observed several patches of secondary BSRs, as you can see in the lower left panel. Next slide, please. So we have conducted 3D modeling of the base of gas hydrate stability zone, and we have also analyzed the 3D geometry and reflection characteristics of the double BSRs. So we have identified different potential mechanisms for their formation. As you can see from the first row, in the Tohini Basin, we have observed BSR2, the deeper BSR that mimics the shape of an unconformity at the base of the Tohini Basin. And from our modeling work, and we have shown that these deeper BSRs are paleo BSRs that formed before the rapid sedimentation in the basin. At 3 thrust ridges, we have observed subparallel double BSRs, and we propose 2 alternative mechanisms. The first is we have shown through modeling that these BSRs can be caused by tectonic uplift at a rate of 3 to 5 millimeter per year. And this rate is pretty high, and we think it is related to subducting seamount at this margin, which can divert slip on the plate interface to upper plate splay faults. Alternatively, these subparallel BSRs can be related to pressure cycling caused by fluid migration associated with slow slips that occur frequently along this part of the margin. In the third location, we have seen in the bottom row, as you can see, those double BSRs, they are separated by 60 to 120 meters beneath the ridge flank, and they converge to the peak of the ridge. And we have shown that these double BSRs can be caused by heat advection related to fluid migration, and the fluid migration the fluid can migrate through those highly dipping sedimentary strata. So our study has demonstrated that the formation of double BSRs is closely related to subduction processes along the northern Hikurangi margin, and double BSRs can be used as indicators for areas with recent sedimentation, tectonic, or fluid activities. So you can check out my poster for more details, and we also published a paper earlier this year in EPSL. Please check it out. Thank you.
Excellent. Thank you, Shuoshuo. All right. And last but not least, we have Sean Gulick, who is a research professor at University of Texas Institute for Geophysics.
Thanks very much. All right, just a quick obligatory title slide to thank my co-authors from UT and Caltech. Our cruise logos there, and those are the brave souls that dealt with extremely high wave heights south of New Zealand. So next slide. Okay, so I'm just going to do a quick tour of what we learned on the CC project, where we're studying the Pusiker basically subduction initiation study. So the southernmost profile, which is the one that has the yellow dots representing OBSs, which is CC line 1, is in a paper submitted by Brandon Shug, and you can see it on the very bottom there. And what it basically shows is subduction having initiated, but not a very significant amount of sediments having accreted to that margin, but still you can see some evidence of thrust faults, as well as the through-going Pusiker fault, which was a strike slip fault that was actually present prior to the subduction starting. And that's going to be the key point of this talk, or of this poster. And if you go to the next line up, which is CC line 2, it's the next one that has OBSs on it. You can now see that there's a significant amount of accreted sediments in this section, but it's interesting because you can see both thrust faults mostly in sequence, but you can see some you might start thinking of as out of sequence. And you can see that there's significant amount of some degree of potential strike slip motion within the forearc, but then clearly strike slip acting as a backstop as well. And again, that's the same through going original strike slip feature that was present before. And then if we go to the northernmost portion, which is a reprocessed Ewing 1996 line in PSDM, and it's just barely visible right above the yellow dot covered line. And again, you can see an accreted section there. And again, it's largely backstopped by strike slip. And the line that I haven't shown you here, but it's on my poster, is the northernmost line, CC line 8, which has just a continuous series of strike slip faults. And so we put this kind of set of observations in context. And on the next slide, this is just a model that is a modified model, actually some earlier papers by Brandon Schuch, which basically shows the evolution of this system. And the point that I want to make, and I think that's really important to think about, is this was first a strike slip margin. And then over time, due to changing plate configurations, we started an oblique subduction zone that is more advanced to the north. It's had longer to accrete, and it's had more sediments, probably coming from Fjordland, going down into the axis of the trench. And so, we can argue that definitely the subduction has initiated. We can argue it initiated the long strike slip at a contrast between continental and oceanic crust. That there's some uncertainty in the exact timing of the accretion of the sediments present, but probably sometime between mid-Miocene and Pleistocene. That the strike slip fault clearly predates the subduction, but it's still present. It's now actually basically accommodating strain partitioning. So we have both accretion and strain partitioning happening on a feature that's older than the subduction zone. And so this leads to an interesting question: how many of these strain partitioning features do we see in various subduction zones might actually predate their subduction zones if that's what they originally initiated on? And maybe that's just these pre-existing zones of weakness persist for substantial periods of geologic time through multiple types of plate boundaries. And I'll stop there. Thanks very much.
Excellent. Thanks so much. Yeah, thanks to all of our speakers. That was fabulous. So now I'm to make this a little more dynamic, gonna stop sharing. I'm gonna try to stop sharing. Oh, here we go. I can see all of you. So yeah, thanks to everyone. And yeah, we'll open it up for questions. If anyone has any, yeah, if you do, please just pop it in the chat. Maybe while we wait for, I have some questions. So now selfishly, oh, there's some other questions coming in. So first I'll go to Gail, who has a question for Edgar.
Yeah, so I know there will be some upcoming drilling in the region where you collected your data. And did any of your profiles cross the drill sites? And did you learn anything that might affect the drilling or be enhanced by the drilling?
Yeah, actually, I think the drilling are actually they're actually gonna happen on the flanks of Valdivia Bank. So it won't actually go right into the expanded sediment section of the rift grabens. But I think there's still a lot that we can learn just from getting ages of certain key horizons on the sediment packages to the flanks of Valdivia Bank that we might be able to tie it into those grabens, at least a lot better than I can now, because I'm pretty much just estimating ages based on sedimentation, accumulation, and other sites that are a lot farther from the seamount. But yeah, definitely looking forward to that upcoming cruise.
Great. Thank you.
So next, Anne Bissell has a question for Rob, and then I see that Pat has his hand up. So we'll do Anne, Jenny Collier, then Patrick Hart.
So thank you, Rob, for sharing with us these new exciting results. So I looked at your presentation and your interpretation with all the faults. So my first question is, like, most of the faults you didn't interpret them up to the sea floor. Why is that? And how do you differentiate between bending fault or compaction fault across basement high?
Yeah, so I don't show it in that presentation, but if you zoom in on a kind of, because of the amount of topography that we have on the basement, there's undeniably some of that faulting is kind of variable compaction, the result of that. But if you zoom in on the easternmost part of the profile, there clearly is quite step up in the kind of density and a reduction in the spacing of the normal faults on the incoming plate. But like you say, most of the faults in the sediment really aren't very high offset. And that's why in a lot of cases, I don't even pick them all the way to the seabed, because once you get into the very soft sediments at the seabed, there's really kind of no indication that there's any offset there at all. And I kind of get into this a little bit in my presentation, is that really we're not dealing here with these kind of very high offset bend faults. And even though there is a slight increase in the density of faults, really we have to say that in order to get this very high level of hydration, it has to be dependent on the pre-existing basement fault structure, because we're not creating a new generation of faults that you'd see in the sediment.
Do you see their flows like increasing towards the trench?
Yeah, so yeah, the density, certainly the density of the faults increases towards the trench, but the offset, not particularly.
Thank you.
No problem.
All right, next, Ginny Collier had a question for Adam.
Sorry, can you hear me? Oh yeah, okay.
Well,
So Adam, so sorry, I haven't done my homework and I haven't looked at your poster, but I was interested in your, if you could tell us a little bit more about how you were getting shear wave splitting measurements, so what your acquisition was and what data you were using.
Yeah, sure. So the experiment was conducted with an array of OBS, and we're recording on the geophones, on the horizontal geophone components. Now, a whole range of different seismic sources were shot into these instruments, because one of the goals that was set out in this study was to try and understand or try and see if we can observe any frequency dependence of anisotropy to do with fracturing, and that idea comes from Mark Chapman in Edinburgh, who we work with, who has a series of models which explain the difference when you're imaging fractures, because if you have you know, a small number of big fractures or a big number of small fractures, they can appear the same if you don't probe them with different kind of seismic wavelengths. So when the experiment was done, there's two airgun sources, Bolton GI airguns, which give us frequencies in the range of kind of 10 to 200 so hertz. But we also have two Sparker sources, which give us frequencies looking, more sort of a couple of hundred hertz up to a kilohertz, maybe 1.5 kilohertz. Now, at the same time as doing the anisotropy experiment, there was lots of other things being done using the sources, using streamers, and recording lots of things at the same time. So we do have a bit of a trade-off in some of the data sets between the idea of getting lots of things. So one of the next things I'm going to be doing is because I've been looking at the airgun data, is to look at the Sparker data and see if we can see any differences. And well, I'll hopefully report on that at a future meeting.
So just to follow up then, so you're getting good conversion up the soft sediment in the North Sea.
Yeah, I mean, it really, when you look at these records, when you look at the horizontal geophones and you rotate into a radial and transverse component, you see that the thing is just stacked full of shear energy. It's really it's a really quite remarkable signal that we can't really explain in any other way. There are some really quite distinct stratigraphic contrasts, and they're probably going to be the key places where we're getting conversion. But there's definitely looks to be shear energy in there.
Great, thanks.
Great. So next, I'll invite Pat Hart to ask a question since he raised his hand.
Thanks. This is a question for Shuoshuo regarding the double BSR poster. And I did look at your poster, And I noticed in the poster, but not in the slides that you showed, you did show a possible explanation, what you called the steady state explanation, where the two BSRs, the upper BSR being structure 1 hydrate, the more widespread, and then the lower BSR being a structure 2, less widespread, so heavier gases. And in the double BSRs that I've looked at around the world, but not really quantitatively, I've always leaned towards the structure 1, structure 2 explanation, because I've always kind of been struck by the interval between the upper BSR and the lower BSR is always about the same, 50 milliseconds, 60 milliseconds. And though I don't know that that would correspond to the stability zone for structure 2 hydrate, I'm wondering if you looked at that as when you were considering your steady state model, and really what pushed you away from that structure 1, structure 2 to the uplift and other explanations that you had for your lower BSR.
Okay, Patrick, thank you for your question. So I will answer it in 2 parts. So first, we have drilling data in this margin, and we have recent expedition 372 and 375, and plus we had numerous previous drilling with relatively shallow holes. And from all these studies, we haven't seen like deeper seen like a lot of higher order hydrocarbons. So they the gas composition is dominantly methane. So we think the hydrate in this part of the margin is dominantly structure one hydrate. And the part 2 of my answer is you mentioned like what the double BSRs, like you have observed, has a constant, almost constant separation between the two BSRs, but that is not the case in our observation. For example, in our basin case, we have observed the BSR2 is deeper than the BSR1 by 100 to 360 meters, and their separation are not constant, but they're diverging. And similar as what we saw from the last example I show, like those two BSRs, they are separated by like 60 to 120 meters, then converge to the peak of the ridge. So it is hard to explain if you have this composition difference, why they would have this geometry, 3D geometry that actually does not follow the stability zone that should be more constant, the separation between those two BSRs. So I think from our analysis for the 3D geometry and also comparison to the unconformity at the bottom of the basin, we think these double BSRs are more like structural and are not caused by different gas composition.
Oh, thank you. Yeah, that geometry, the geometry argument, I think is pretty strong. I may still hold on to the structure 1, structure 2 for an explanation in other places, but yeah, with your drilling data and the geometry, I think that's a very strong case. So thank you very much.
Great. So next, I believe Brandon Shuck had a question for Rob.
Yeah, thanks. Yeah, I have a couple questions, and I guess it looks like Ann Trehu actually kind of stole them in the chat. But I was wondering about the MOHO in these models. How well is the PMP phase? Is that super bright across all these data records? And was this MOHO like a boundary incorporated in your model? Because there's not really any sharp velocity changes across there. And I guess if there's a lot of serpentinite, you might not expect there to be a bright MOHO reflection anyways.
Yeah, so the nature of the Tommy 2D model is that it's essentially a continuous velocity mesh with no hard breaks. And that's kind of what we wanted anyway, because in this kind of scenario where you have, hydration of the lower crust and upper mantle, and particularly in slow spreading crust where you might expect, say, peridotite to be placed up into the crust through detachment faulting and stuff like that, there's quite a good chance that break maybe wouldn't be as hard as you'd like. But yeah, PMP is fairly well imaged on the OBS data. And actually, when we trace the rays through the final model, we see quite a nice division between the rays we picked as PG above that line and PN below. I know that with the quite low velocities we're seeing, that it's quite natural to think, have we got that reflector too high? And it's definitely something that I've thought about. But between the PMP picks and the ray tracing, I'm fairly confident that that is a true reflection of the MOHO.
Okay, yeah. It's interesting if you were to follow like a constant velocity contour, it looks like the same thickness as you go down there. And my other question was related to that, I guess, Anne stole as well. I was really intrigued by all these patterns of the sediments. If you look, there's some super interesting on-lap variations that I think are kind of different from what you see in most overlying ocean crust. So if like where you have the crust getting thinner, you actually have downlapping of the sediments, or actually, I guess if you reverse the bending, it's sort of onlapping. So I was wondering if you could comment on the relationships between the stratigraphy and the evolution of the crust.
Yeah, so you can quite clearly see certainly the first two layers of sediment, so through to kind of, and I'm just trying to remind myself of the dates here. So yeah, you can't see it so well in this part of the slide, this part of the section, but on the easternmost part of the profile, so the oldest sediments on the incoming plate there are kind of Cretaceous in age, and then through to the present. But sediments as young as, say, the Miocene, Pliocene are still quite clearly being affected by the basement topography. So, you know, both this basement topography probably wasn't fully covered by sediment until quite a long time after the crust was formed. And to be honest, I haven't really thought about those sediment relationships in an awful lot of detail, but it's quite clear, I think, that, you know, essentially all this basement topography existed prior to the ridge, prior to the outer rise, and it has affected the deposition of sediments quite a lot.
Great.
I don't know if that answered your question, but I hope that kind of.
Anne, did you have anything else that you wanted to ask or add along those lines?
No, not really. I look forward to seeing more from that experiment. Looks like a spectacular data set, and thank you, Rob.
Actually, I have one more question for you, Rob. I thought it was there was an interesting change in morphology of the basement between your thinner crust and your thicker crust, and it was the opposite way that I would have expected. It seemed like you had more smaller faults in your 5 kilometer thick crust, but kind of larger topography in the thicker crust. So I was curious if you could comment on that.
Yeah, so that's something we've just started thinking about ourselves, actually, because like you say, it does seem to go the opposite way. So in the kind of thicker, more magmatically robust crust, we seem to have this much more kind of blocky topography, which is kind of on the order of tens of kilometers. And then within this thinner crust that we interpret, we have kind of these much smaller offsets. The basement's still very rough, but you don't see these kind of kilometer scale pieces of topography in the basement. Yeah, we haven't really kind of got a nice solution to that yet. We don't know whether it's just that we're, you know, lucky in that regard, that we've kind of happened to catch a section that looks like this. Obviously as well, you can't see it on the section that's just prior to the outer rise, but actually once you get below the décollement, there's quite a lot of topography on the basement beneath the accretionary prism, which we also interpret as this kind of 5-6 kilometer thick crust. So even though there doesn't happen to be this quite steep topography in that kind of 50 kilometers prior to the outer rise, it does exist deeper down in the profile.
Interesting. So we still have a couple more minutes for questions, and I have more for multiple people, so I'll carry on. But yeah, please, if you have other questions you'd like to ask, put them in the chat. I had a question for I guess for Sean and Brandon. It's been really exciting to see the results of the, I'm never going to be able to pronounce the name of the Perseguir bridge.
Pusiger.
Thank you. But so it's been interesting to see your evolution of strike slip to subduction. And you, at the very end of your presentation, Sean, you mentioned that this might be a common evolutionary phase and something seen other places. And I was curious if you could put your finger on any other kind of oblique subduction systems with prominent strike slip faults where there was any timing information that they might have formed.
Well, yeah, actually, I really meant that to be a query for us to think about, because I don't actually have an example right now that we're certain that the strike slip came first. But I do, since it's favorable for subduction to initiate along strike slip plate margins, then we might envision that this kind of scenario that we've now imaged in a very young subduction zone at Pusager could be true elsewhere. And the problem, of course, is that, you know, once this whole thing develops into a good subduction zone with a very nice 4-arc sliver and a through-going strike slip system, how do you know whether it was there before or not? And I think maybe we should, now that we know that it's certainly happened here, it'd be good to go back and look at some of the evidence of, you know, median tectonic line in Japan, or, you know, the Sumatra fault.
Sumatra, yeah. I didn't know if the big basins associated with the strike slip faulting back behind Sumatra might have give a indication of timing that one could compare with.
Yeah, no, I think it'd be really worth investigating that in much more detail. I don't know for sure yet, but certainly going to take a look. And if anybody does know of one that predates, please let me know. Great.
And then I actually had one more question for Yu-Huan. You showed these beautiful images of the pre-stack depth migrations of this collisional zone. And I love that you called it the data from 2009 legacy data. So that shows what an old timer I am. But you showed the images, but I was curious about the velocities, and in particular, if you had low velocities along the kind of underthrust sediments along the boundary of your collision.
Yeah. Yes. So actually, for long pre-step depth migration, we spent a lot of time to build a velocity model. First, we get our initial model from the staking velocity analysis, and later we need to interpret the seismic data from time session, and then we interpret the sediment layer and assign the sediment layer a velocity from our observation from OBS data or from staking velocity analysis. And then we can assign each layer a constant velocity, or the velocity can be changed from vertical or horizontal. And then after we build the velocity, which is more fixed geological model, and then we use this velocity to run the pre-step depth migration. And also it's also before run pre-step depth migration, we really need to remove the multiple, because once a lot of important deeper structural spatial detachment usually cover with multiple.
Okay. All right. Well, thank you. So I think we're at the end of our time. So I just want to encourage everyone to go look at the posters, and we can continue the conversation. And through the Pathable website, there's a chance to chat or set up times to talk to people. So so that would be that'd be great. But thanks for all the wonderful presentations and conversations. This was fun. And join us in 30 minutes if you care about rifts and volcanoes, and who doesn't. So all right.
Thanks, Donna.
Thanks, everyone.
Thank you, Donna.
Bye-bye.
Thanks, Bill.
Thanks.